All right, let's wait until this preview comes up. Perfect. Audio is working. Good. Share out our channel. To Twitter and Denver Devs channel. I wish it remembered the last channel. It's always a pain to have to like type in topic Twitch, but it doesn't take too long. All right, got a few minutes left before officially starting, so let's go ahead and get set up. I don't have to use that keyboard. I've got this one down here. All right, so to hub. Learning Rust there. Let's see where we're at. Chapter 10, Validating Reef References with Light. This, I believe, is the last part of Chapter 10, right? Yeah, and then we're going to get on to testing and then actually building stuff. So that's going to be pretty cool. Lifetimes. Let's we'll cd into Chapter 10. Cargo. Perfect. We'll be in main. We'll have this open. So when we want to when we're ready to begin updating, we're all ready to go. One minute left. Curious if the stats and the phone dashboard. Refresh this so it actually shows that we're online. Apparently we're offline. That's a fun thing with the apparently we're offline. Oh, and we need to pause you again. All right. Well, I'll just ignore you for right now since you're not going to tell me any interesting information. All right, but it's 7 o'clock, and that means it's time to start going through the Rust book again. So let's do it. This time we're on Chapter 10. We are working with validating references with lifetimes. All right, so to continue on. One detail we didn't discuss in the references and borrowing section in Chapter 4 is that every reference in Rust has a lifetime, which is the scope for which that reference is valid. Most of the time, lifetimes are implicit and inferred, just like most of the time types are inferred. We must annotate types when multiple types are possible. In a similar way, we must annotate lifetimes when the lifetimes or references could be related in a few different ways. Rust requires us to annotate the relationships using generic lifetime parameters to ensure the actual references used at runtime will definitely be valid. The concept of lifetimes is somewhat different from tools in other programming languages, arguably making lifetimes Rust's most distinctive feature. Although we won't cover lifetimes in their entirety in this chapter, we'll discuss common ways you might encounter lifetime syntax so you can become familiar with the concepts. See the Advanced Lifetime section in Chapter 19 for more detailed information. So from one of the other Rust developers that I know, he told me, I mean, he's been learning and going through Rust too, and he said that that he's found that every time he pulls out lifetimes where he feels that he has to use them, he ends up being wrong, and that if he reworked his code to not need lifetimes, things are better. So that's a very, like, it's an interesting thing. I think what ends up happening is that a lack of using or choosing to use lifetimes makes it so that he has a headache later in the future, almost like technical debt. But we'll see if we run into those ourselves or how they end up working. All right, lifetimes prevent dangling references. The main aim of lifetimes is to prevent dangling references, which caused a program to reference data other than the data it's intended to reference. Consider the program in listing 1017, which has an outer scope and an inner scope. So we have let r, so we're creating a variable r, let x equals 5, r equals to the reference of x. But as soon as this block is done, x, which is on the stack, will be sort of unmounted from memory, like removed and released. So yeah, this reference won't be good anymore. Because it will be referenced to a null area memory. Note, the example in listing 1017 and the next few examples declare variables without giving them an initial value. So the variable name exists in the outer scope. At first glance, this might appear to be in conflict with Rust having no values. However, if we try to use a variable before giving it a value, we'll get a compile time error, which shows that Rust indeed does not allow null values. Basically, what Rust is doing here is it's saying, hey, you're going to be using a variable, so I'm just going to go ahead and wait for the type system until you actually use it. And then I'll just, like, everything will be figured out. But if you never use it, that's an error. The outer scope declares a variable named r with no initial value. And the inner scope declares a variable named x with the initial value of 5. Inside the inner scope, we attempt to set the value of r as a reference to x. Then the inner scope ends, and we attempt to print the value of r. This code won't compile because the value r is referring to has gone out of scope before we try to use it. Here is the error message. Okay, so x does not live long enough. Sometimes it says, like, consider using lifetimes here. The variable x doesn't live long enough. The reason is that x will be out of scope when the inner scope ends on line 7, but r is still valid for the outer scope because its scope is larger. We say it lives longer. If Rust allowed this code to work, r would be referencing memory that was deallocated when x went out of scope, and anything we try to do with r wouldn't work correctly. So how does Rust determine that this code is invalid? It uses a borrow checker. The Rust compiler has a borrow checker that compares scopes to determine that all borrows are valid. Listing 1018 shows the same code as listing 1017, but with annotations showing the lifetimes of the variables. Alright, so let r, let x equals 5, r is equal to x, so we can see that we have lifetime a. I'm not really sure how that is. Annotations of the lifetimes r and x named a and b respectively. Okay, so this is the lifetime a, and then we have x equals 5, so this is lifetime b, and we can see that lifetime b ends right here. And then r will be destroyed here, which is lifetime a. Here we've annotated the lifetime of R with quote A and the lifetime of X with quote B. As you can see, the inner B block is much smaller than the outer A lifetime block. At compile time, Rust compares the size of the two lifetimes and sees that R is a lifetime of A, but that it refers to memory within a lifetime of B. The program is rejected because B is shorter than the A. The subject of the reference doesn't live as long as the reference. Listing 1019 fixes the code so it doesn't have a dangling reference and compiles without any errors. Right, so this is sort of like the way to rewrite the code so it doesn't have the same problem. So let x equals 5, let r equals reference to x, print line r. So we can see now, okay, A and B are living almost exactly the same time. There's only one line difference, which is when they were declared. Here, X has the lifetime B, which in this case is larger than A. This means R can reference X because Rust knows that the reference in R will always be valid while X is valid. Now that you know where the lifetimes of references are and how Rust analyzes lifetimes to ensure references will always be valid, let's explore generic lifetimes of parameters and return values in the context of functions. Good morning. Welcome to the stream. Miguel, yes. I have to remember your name because it's not quite exactly the same as your username. And also I'm not sure how to pronounce your username. Generic lifetimes and functions. Let's write a function that returns the longer of two string slices. This function will take two string slices and return a string slice. After we've implemented the longest function, the code in listing 1020 should print the longest string is ABCD. So here you go, function main, let string 1 equals string from ABCD. So this is like a full string on the heap. Let string 2 equals a stir XYZ. So this is on the stack. Let result equals longest string 1 as string as stir. So converting it from on a heap to on the stack, and then string 2, which is already there. Print line, the longest string is, and then result. Note that we want the function to take string slices, which are references, because we don't want the longest function to take ownership of its parameters. We want to allow the function to accept slices of a string, the type stored in the variable string 1, as well as string literals, which is what variable string 2 contains. Refer to the string slices as parameter section in chapter 4 for more discussion about why the parameters we use in listing 1020 are the ones we want. If we try to implement the longest function as shown in listing 1021, it won't compile. So, stacking, welcome, good morning. Twitch is finally working again. I wasn't aware it wasn't working, so I'm glad that it got fixed in time for this morning's stream. Okay, so this saying this won't compile. So function longest, it takes x, which is the reference to string, y, which is a reference to string, and returns a reference to string. If x.length is greater than y.length, x else y. It looks like my low latency mode is working too. Yes, that's good. Instead, we get the following error that talks about lifetimes. So let's go ahead and set this up, which is we're going to write the code that uses longest, and then we're going to write the longest function. So we're going to create one that's a string on the stack heap, and one that's on a heap. So let's come into here, and we'll do let stream 1 equals string from, and it's like Hello world. Let string 2 equals, and this is just going to be a stir, so it's ABC. So you're not stream 1, string 1. Did I stream yesterday? Yes, I streamed yesterday, but I ended up allowing myself to sleep in a little bit and started the stream at 9:30 a.m. But then I went for 2 hours. So I have uploaded to YouTube, but I haven't added it. I'm behind for a few videos and streams on adding them to the playlist. So hopefully I'll be doing those in the next, like hopefully today. Okay, so string 1, string 2, then we want to compare this, like run a compare. So we're gonna get longest, that's what we're doing right here, right? Result equals longest, and then, okay. Result equals longest, and we're gonna pass in string 1 dot as stir, as not mutable stir, just as stir, and then string 2, and then we can print line longest string is, and we'll put in result. So then we'll have now our function result, and this is going to take in a string 1, which is a reference to a stir, and string 2, which is a reference to a stir, and we're going to return back a reference to a stir. And so in here, we're just going to compare the two. So if string 1 is greater than string 2, and I guess it's going to be longest, right? So string 1 dot length is greater than string 2 dot. So then return string 1, else return string 2. Expected lifetime requirement in the type of string 2. So let's take a look. Expect explicit lifetime requirement in a type of string 1. Lifetime static required. So, function longest. That should deal with that problem. Then here, missing lifetime specifier, expected lifetime parameter. This function's return type contains a borrowed value, but the signature does not say whether it's borrowed from string 1 or string 2. So we don't know which one this is coming from. I think that's the really interesting thing here. So yep, this does not say whether or not it's borrowed from string 1 or string 2. So I think what the idea is that it doesn't know, like we bring this as a string, and we bring this in. Now they're both references here, but they're not exactly equal as references. Explicit lifetime required in the type of stir 1. Consider changing the type of stir 1 to a static stir. And this one is the same thing. It needs the lifetimes for both of them. Note that we want the functions to take string slices, which are references, because we don't want the longest function to take ownership of its parameters. We want the function to accept slices of a string, the type stored in the variable string 1, as well as string literals, which is what the variable string 2 contains. Refer to the string slices of parameter section in chapter 4 for more discussion about why the parameters we use in listing 1020 are the ones we want. If we try to implement the longest function as shown in the listing 1021, it won't compile. This is the one we have essentially. Instead, we get the following error that talks about lifetimes. The help text reveals that the return type needs a generic lifetime parameter on it because Rust can't tell whether the reference being returned refers to X or Y. Actually, we don't know either because the if block in the body of this function returns a reference to X and the else block returns a reference to Y. When we're defining this function, we don't know the concrete values that will be passed into this function. So we don't know whether the if case or the else case will execute. We also don't know the concrete lifetimes of the references that will be passed in. So we can't look at the scopes like we did in listing 1018 and 1019 to determine that the references we return will always be valid. The borrow checker can't determine this either because it doesn't know how the lifetimes of X and Y relate to the lifetime of the returned value. To fix this error, we will add generic lifetime parameters that define the relationship between the references so that borrow checker can perform its analysis. So the lifetime annotation syntax. I remember I sort of played around with this a little bit before when I was running into these problems, and while chat was helping me get through it, and they're like, "Oh, just add in some lifetime parameters," and it was we refactored the code in the end, which made it easier to read and a lot better. And I was really confused by like the single quote and the static and like the other weird characters. So I think this is going to be a little bit easier to understand. Like I'm now actually understanding from that previous graphic that this is literally how it's seen it in the borrow checker. Lifetime annotation syntax. Lifetime annotations don't change how long any of the references live. Just like functions can accept any type when a signature specifies a generic type parameter, functions can accept references with any lifetime by specifying a generic lifetime parameter. Lifetime annotations describe the relationship of the lifetime of multiple references to each other without affecting the lifetimes. Lifetime annotations have a slightly unusual syntax. The names of lifetime parameters must start with an apostrophe and are usually all lowercase and very short, like generic types. Most people use the name apostrophe A. We place lifetime parameter annotations after the ampersand of a reference, using a space to separate the annotation from the reference's type. Here are some examples. A reference to an I32 without a lifetime parameter, a reference to an I32 that has a lifetime parameter named A, and a mutable reference to an I32 that also has the lifetime A. One lifetime annotation by itself doesn't have much meaning because the annotations are meant to tell Rust how generic lifetime parameters and multiple references relate to each other. For example, let's say we have a function with a parameter first that is a reference to an I32 lifetime A. The function also has another parameter named second that is another reference to an I32 that also has the lifetime A. The lifetime annotations indicate that the references first and second must both live as long as that generic lifetime. Yeah, so it's just it's this like single quote that really gets me. So is that saying the letter after the single quote doesn't matter? That's kind of how I just read it, and I'm not completely sure. So like the other thing is in this graphic here, we have, okay, so R is like we can assign it that this is A and this is going to be B. And so I kind of wonder, can we write this code and tell it that it's going to be part of A. So I kind of want to try that before I like actually get the real stuff. So let's go ahead and not worry about this right now. And let's run with the other one. I think what I can do is I can create a function to sort of like using lifetimes this. And what we're going to do here is have a function lifetimes. What are you yelling about? Not find function. That's fine. So you're not going to take anything in. You're not going to return anything. What we're going to say is let A. We're not going to do anything with you. Then we're going to have a block in here and say let B equals 5. And then A is going to equal now to a reference of B. I'm not going to use the lifetimes yet. I want to make sure we get the same error. And then we're going to print line A is A. Okay, so if we run this, we should run into this B does not live long enough. Borrowed value does not live long enough. And let's see what the actual error message says. Cargo run. Borrowed value does not live long enough. B dropped here while still borrowing. So I love how it actually is able to tell me, okay, here's where B was removed from memory. Borrowed value needs to live until here. So if I were to say, let A, and I do what, single quote A, like that. Expected colon found B. Wait, how does this work again? A reference with an I30. Oh, so hold on. It's B equals, no, B. I think it's here. It's colon, reference symbol, single quote A. Expected type found equals. Oh, we have to give it a type too. What is this? I32? Type ascription is experimental. See issue. So are we not allowed to do that? Or is it more of like we want a here? Do okay. So we're going to create this here. We don't need to do that here because it already exists. Use of undeclared lifetime A. Undeclared lifetime A. Okay, interesting. And then B, we want to set this also to be using lifetime A. Use of undeclared lifetime A. All right, well, clearly I don't know how to actually do that. Okay. Lifetime annotations and function signatures. Now let's examine lifetime annotations in the context of the longest function. As with generic type parameters, we need to declare generic lifetime parameters inside angle brackets within the function name and the parameter list. The constraint we want to express in a signature is that all the references in the parameters and the return value must have the same lifetime. We'll name the lifetime single quote A and then add it to each reference as shown in listing 1022. So function longest, oh, interesting, turbofish syntax to give it the A there. So can I do that here? So it's like that. Expected one of colon the, well, no, so it doesn't like that either. However, it wants us to put this in the longest. So longest is lifetime A, and then all of these are through lifetimes A. So if we get rid of this function, and we bring this all back, then what we're going to do is we're going to say, okay, well, this is not living long enough. So instead, this will be lifetime A. But now we have to say, okay, string 1 is going to have a lifetime of A. And string 2 has a lifetime of A. And the return string has a lifetime of A. I can see how this is just adding a bunch of complexity in here. So now you have to keep this in your, on our minds too, of what's really going on. This code should compile and produce the result we want when we use it with the main function in listing 1020. The function's signature now tells Rust that for some lifetime A, the function takes 2 parameters, both of which are string slices that live at least as long as lifetime A. The function's signature also tells Rust that the string slice returned from the function will live at least as long as lifetime A. These constraints are what we want Rust to enforce. As discussed earlier, by specifying the lifetime parameters in this function's signature, we're not changing the lifetimes of any values passed in or returned. Instead, we're specifying that the borrow checker should reject any values that don't adhere to these constraints. Note that the longest function doesn't need to know exactly how long x and y will live, only that some scope can be substituted for A that will satisfy the signature. So this feels like somewhat similar to like the generics, where we're saying, hey, make this a generic function, so like write the other versions of it, but only write it if they fit the following parameters. So in this case, we're doing the same thing. We're like, only allow certain things in if they're going to live long enough. Otherwise, reject them. So if I'm understanding this correctly, I'm guessing you're giving the function a lifetime of A. So you're saying all stir will live as long as the function. That's what I think I'm doing. But the wording they're also using is saying that we're not actually changing the life of anything. We're just telling them to reject, like, don't allow this function to be passed in anything that wouldn't last as long as A. And I think because the Rust compiler is so strict, it's saying, hey, well, what if you were passed in something else that didn't last that long? We better prepare for that too. Also, the other thing is I want to verify the theory, which is if I put this as B, will it still work? Yes, it still works. So it's literally anything, and I think it can be any lifetime, like any string. So if I do like hello, that should still work too. Yeah. Okay. Not that we actually want to do that. A is fine. When annotating lifetimes in functions, the annotations go in the function signature, not in the function body. Rust can analyze the code within the function without any help. However, when a function has references to or from code outside that function, it becomes almost impossible for Rust to figure out the lifetime of the parameters or return values on its own. The lifetimes might be different each time the function is called. This is why we need to annotate the lifetimes manually. When we pass concrete references to longest, the concrete lifetime that is substituted for A is the part of the scope of X that overlaps with the scope of Y. In other words, the generic lifetime A will get the concrete lifetime that is equal to the smaller of the lifetimes of X and Y. Because we've annotated the returned reference with the same lifetime parameter A, the returned reference will also be valid for the length of the smaller of the lifetimes X and Y. The returned reference will also be valid for the length of the smaller of the lifetimes. So was the problem really this right here? Was that we were returning a reference here and it potentially wasn't living longer? It was like living longer than these. And so we're saying like, hey, as soon as these die, this will die too. I'm kind of wondering. I think part of it is I'm still like fully unsure about the lifetimes. I wish that there was a plugin for Visual Studio Code that can like I could see it. Let's look at how lifetime annotations restrict the longest function by passing in references that have different concrete lifetimes. Listing 1023 is a straightforward example. So in main we have we have our let string from long string is long, okay. Then in a block we have let string to string from XYZ. Let result equals this, print line, longest string is. Yeah, I feel like something showing you lifetimes and ID would help me also. So there's some really cool visualizers that have been written for like JavaScript and Python and sort of like the references and what's really going on in memory behind the scenes. It would be really awesome if that could be made. I'm not, since I don't understand it that well, I don't think I can write that, at least not right now. Maybe someday in the future, but I could definitely see that being a helpful learning resource. Okay, so if we update this, what we're doing is we're saying, okay, this first one is going to be out here. Then we're going to have a block. Actually, we do want this tabbed in. Nope. There you go. So because this block, as soon as this block ends, then these will be destroyed from memory. So this has like an implicit lifetime of, let's say, A, and these have an implicit lifetimes of B. So we're telling it, don't allow anything to be passed in unless they have the same lifetime. So will this fail now? I'm actually surprised that this isn't, well, let's run it. Let's see what happens. Okay, so that's working still. Let's see what they say about this. In this example, string 1 is valid until the end of the outer scope. String 2 is valid until the end of the inner scope. And the result references something that is valid until the end of the inner scope. Run this code and you'll see that the borrow checker approves of this code. It will compile and print the longest string is long, string is long. Next, let's try an example that shows that the lifetime of the reference and result must be smaller than the lifetime of the two arguments. Let's try an example that shows that the lifetime of the reference in result, so that's this one, so whatever is passed into result, must be smaller. So we saw that sort of like the graph where it's like, okay, must be smaller, meaning that it must be created and die within the lifetime of everything else. Then the two arguments. We'll move the declaration of the result variable outside the inner scope, but leave the assignment of the value to the result variable inside the scope with string 2. Then we'll move the print line that uses result outside the inner scope after the inner scope has ended. The code in listing 1024 will not compile. So here we're also declaring result up by string 1, and then we're doing our print down here. So inside of our block, we are getting result. So lifetime begins here, I believe, and ends here. String 1 is also just as long as result. String 2, lifetime is created here and dies here. So if we were going to go on like line numbers, so this is like string 1 is 1, 2, 3, 3, 4, 3, 4, 5. This is 1, 2, or I don't know, because I feel it dies on the closing. So if we do the opening too, it's like 1, 2, 3, 4, 5, 6, 7, 8 is this lifetime's value. Result would be 7. This one would be 1, 2, 3, and result would now is the same as the 8. So it's going to be longer, and it's going to say, hey, you can't do that. You're using something that's shorter than me, so I don't really have access to it anymore, probably. Print line the longest string is. So let's try this. So we're going to remove result. We're going to get rid of the let, and we're going to put that up here. So let result. Assign it inside of here. And now to begin with, like this works still because we're using result before this dies. But if we move this down, now we should get an error. Because this print line doesn't happen in the same lifetime. I'm not seeing an error. Let's try running it. Okay. So did I do that incorrectly? The string 1, result, string 2. Oh, string from. Look at what they did. They created this on a heap here. The string 2 is also now a string 1. Now a string on a heap. Mismatch types expected reference to string. So now we have to, are they doing the as stir? They are. So where is that? Results. Are we still doing result in here? We are. So string 2 as stir. Borrowed value does not live long enough, which is interesting. So like string 1, this it lives long enough because it's all the way through here. It doesn't get destroyed right here. Whereas string 2, it runs the function. So the function runs properly because we get the result right here. but we're going to use the result here. It doesn't know which of these two strings are now going to be copied the memory into result. It's just a reference that's going into result, not the actual string. So yeah, then we don't know. The error shows that for result to be valid for the print line statement, string 2 would need to be valid until the end of the outer scope. Rust knows this because we annotated the lifetimes of the function parameters and returned values using the same lifetime parameter, a. As humans, we can look at this code and see that string 1 is longer than string 2, and therefore result will contain a reference to string 1. Because string 1 has not gone out of scope yet, a reference to string 1 will still be valid for the print line statement. However, the compile can't see that the reference is valid in this case. We've told Rust that the lifetime of the reference returned by the longest function is the same as the smaller of the lifetimes of the references passed in. Therefore, the borrow checker disallows the code in listing 1024 as possibly having an invalid reference. Try designing more experiments that vary the values and lifetimes of the references passed into the longest function and how the returned references is used. Make hypotheses about whether or not your experiments will pass the borrow checker before you compile. Then check to see if you're right. Well, of course, the IDE is faster than that. Before I can finish writing it, it will tell me. Wonder, does it tell me? Does it give me any hints of what to do about it? So no, it's not saying that you could do something with this. Now, can I do something like string 2 is B? And use of undeclared lifetime name B. Oh, do we have to, is this where it's declared? Now A is undeclared. Can I do multiple? Lifetime mismatch. This parameter and the return type are declared with a different lifetime. Lifetime mismatch, but data from string 2 is returned here. It's complaining. I'm not sure exactly the syntax to use here, or if it's not even possible. It would make sense if you're only allowed to have a single lifetime. So if we say A here, and then in here we can say, okay, string 1 must be A. Now, if I don't have a lifetime for that, and I just put a lifetime in for A, will this work? Oh, you put a quote around everything. I didn't want you to do that. Missing lifetime specifier for here. So because I use it in little areas, explicit lifetime required for the type of string 1, consider changing the type of string 1 to % a string. Explicit lifetime. So if I create an explicit lifetime, I need it for both, for everything. That's the sort of the big deal with this. But now string 2 does not live long enough. So the only thing I can think of at this point in time would be to not return a stir or a reference to a stir. I'm going to need to pass in either something gives ownership. But I think this one would need to be a string to give ownership to result, and then these would both need to be .to strings. So that way it takes this in, and at this point in time, do we even need these? Probably not. yeah, we don't even need lifetimes anymore. We just take the small hit from creating something on the heap and say, hey, this makes it a little bit easier to read because, hey, we're going to create a new area in memory just for this, and then it all dies here and releases that area of memory, but there's a new one for us right here. So I think this is what was being mentioned to me by another Rust developer, which was if we're using lifetimes, there's a better way. Not necessarily memory efficient better way, but readability way and like technical debt way potentially. I'm not sure if this is the best way to do this, or just not using blocks here would probably be the best thing to do. But if, for example, I had to because of like function calls or something else, I'm gonna go back to make sure that this is in here, so that when I come back and look at it, it's still showing. We need you to be back in here. I doubt the performance hit would be that much kind of undermines the whole point of the borrow checker. Yeah, that's kind of what I'm thinking of, unless we're working with like absolutely ginormous amounts of memory. But personally, I've never worked with anything that big. Result. Oh, it still doesn't like this. String 2 dropped here while still borrowed. Borrowed value needs to live until here because we're saying A. Now, if I remove you, explicit lifetime required for string 1. If I, because I kind of want like this one to be the primary. And so like, hey, make sure that string 1 lives at least as long as string 2, but don't worry about it being longer. Or are we just saying that it has to be the same length? If we remove, we also had the let result in here. Yeah, this works. Now, if I remove the, does this still work? No, okay. So this does need lifetime requirements inside of here because it's saying, hey, we don't know what's going on because they have different lifetimes coming in. So if they have different lifetimes, then the borrow checker freaks out and tells it, hey, you take the wheel, tell me what's really going on. Or tell me how to enforce this. Because I keep on thinking that I want to do something like this, where I want to say like, hey, I want to somehow enforce, or I guess it's not like enforcing, but I want to tell the borrow checker, allow these to be 2 different lifetimes as long as this one is, as long as string 1 is at least as big as string 2, then we're fine. Can I do comma here? So it seems to show that I can do multiple lifetimes here. So if I do U as I wonder if like B, you are A, and you, oh, okay, so I think I understand. I have a hypothesis. So if we assign the first string 1, a lifetime of A, so that's lifetime from here to here. And string 2 is a lifetime of B, and it's a lifetime from here to here. I want to return, and I think this is where it really matters, where I can say, okay, you are going to be a lifetime until here, which is B. So can I just do B like that? No. Yeah, you can do multiple lifetimes. However, the problem is you don't know the lifetime of the returned value. So if I do this one and say, hey, I want you to live until here, lifetime mismatch, this parameter of the return type are declared with different lifetimes. But data from string 1 is returned here. Lifetime mismatch. So it's saying that because of B, so I have to do A. But now string B. So it's telling me that no matter what, the B lifetime cannot be used. It's only a single lifetime. And it's saying no matter what, both of these strings have to have the same lifetime. What I don't understand is that they don't have the same lifetime implicitly, because string 2 dies right here. And string 1 dies right here. That's not the same lifetime. So I guess I still don't fully understand why this works. But maybe I'll be able to find somebody and ask them to explain it to me a little bit more in person. Or maybe it's just gonna be one of those things where I work with it long enough and I'll be able to slowly understand by more of doing it wrong a whole bunch of times. That's probably how it's really going to be. Take a look at how much more we've got. Oh, like half of this document. And it's 1054, so I'm not going to continue on with this, but let's go ahead and update where we're at. So we're thinking in terms of lifetimes. Okay, so this is actually chapter 10 too. 1054. Nope. Yeah, that was completely wrong. 754. I do not live in the ocean. Okay, thinking in terms of lifetimes. Also update here. Okay, so we've updated those. If we come over here, have all of our updates. So working with lifetimes. And gonna send that on up to GitHub. So I have a link to this down below in the description, both to the video on YouTube and also the description of the entire channel here on Twitch. But I will also send, just add this in to chat here, so that way in the chat replay, it's visible to anybody who wants to sort of like go in and take a look at this. I have my Twitter account where I tweet when I go live. I usually go live every single weekday morning at 7 a.m. Mountain Time. I am not going to stream tomorrow morning. But that's because tonight is the Node.js meetup. And so that's actually going to be a really fun one. And I'm I'm going to be the host of it starting, I think, tonight or next month. But we're usually out pretty late, and that means that I'm gonna want to sleep in tomorrow morning. But anyways, we're gonna be talking about the different loaders for Node.js, and also the speaker is Miles Borens, who is actually on the Node.js ecosystem and developing heavily with them. So that's going to be pretty awesome to sort of see and meet him and see how things are going. So if you're interested, I don't know if we're going to be able to stream that one. I have streamed these in the past, but he's also here for Dinosaur.js, which is next week, I believe. And that a lot of times when speakers are near conferences, we don't want to necessarily stream those because it's like a parallel talk to the conference talk, and that diminishes that. But if we end up doing that, I will tweet out. Otherwise, if you're in the Denver area, we'd love to have you stop by. If you're not in Denver because you're in Europe, I am sorry, but we can chat about what we talked about later. And you can always come here. We usually put the slides will be posted as well in this section. So feel free to sort of take a look at that and see what's up. With that, 7:58. It's about time for me to get ready to go to work and actually do real life stuff again. With that, so thanks for stopping by, and I'll see you next time, which is probably Thursday. In my opinion, the lifetimes are not so well explained in the Rust book. I needed a lot of blog posts to finally get it. Jim Blandy and Jason Orendorff's books of Rust do a better job. With the right examples, you'll wrap your head around it. If I could find the stuff to help me out with this, I'll post it on GitHub. That would be perfect. You have access to the wiki, right? So in the Learning Rust, we have this wiki page. We can put like references or like we could create a lifetimes page and then put like, hey, for more reading, go into here. I'll check out the GitHub because I'll be looking out for that myself. Yeah, so either put like an issue or put in a wiki or somewhere. An issue is also nice because I get a notification when that happens. Yeah, that would be awesome. All right, with that, thanks again, and I'll see you on Thursday morning.